Hello students, we're now going to study waves and sound. Now we've talked about vibrations and oscillations. An object can oscillate or vibrate or move back and forth at a frequency f, and f means the number of times it goes back and forth, moving and coming back where it started from per unit of time. And the units are cycles per second, which is also known as hertz, abbreviated Hz for hertz. And the time it takes for that object to go back and forth and come back where it started from, do a full cycle, is called the period. And the units of the period of vibration is seconds. We have that the frequency is the reciprocal of the period, and the period is the reciprocal of the frequency. Now, if the object that's vibrating, that's going back and forth, somehow connects to its environment, if it couples or connects to its environment, the environment is called the medium, then you get waves that will travel through the medium. So the vibrations of the thing that's vibrating somehow connects to the stuff around it. It could be air, it could be water, makes the stuff around it vibrate, and those vibrations move through the material, and those are the waves. So let's have an example. Yeah, sorry, it's a boring example, but at least this one is simple. So let's say I've got something that's vibrating going up and down. It could be a mass on a spring. And let's just say, suppose that this mass was in the surface, a part of the surface of some water or some liquid. And it's going up and down, and it causes waves to propagate through the water, like ripples on the surface of a pond. Now, the way I've got this drawn, I've kind of got a snapshot right here. I've got the very first wave right here, and then I've got the second wave and the third. So you see these waves, they're moving to the right at some speed, some wave speed v, and so sometime, so it started vibrating, and those first vibrations, well, they're here, and it vibrated some more. Oh, that's here, and it vibrated some more. Oh, that's here, and some more. That's here, and now it's in the process of making another wave. So yeah, all right. Now, the waves have the same frequency, right? So if this thing is bouncing up and down at some frequency, I don't know, it could be 100 hertz, let's say, then the waves will also be vibrating up and down at that same frequency, f. Now, the waves that are moving along have a distance from the top of one wave to the next wave, and that's what I'm representing here. That is called the wavelength. So from the top of a wave to the next one, or it could also be from the bottom of the wave to the next bottom of a wave, or it could be from a rising zero crossing. This is called a zero crossing right here, where the wave passes through zero. And well, it's going through zero again here, but this is the downward zero crossing. We need to go all the way to the next upward zero crossing. And this would be a wavelength also. Okay, and now the symbol here is the Greek letter lambda, lowercase lambda. Now, one thing about the homeworks and so on, when I ask you to draw a wavelength, a diagram like this, I want you to get in a good habit. I'm going to be looking for this when I'm grading. I want you to draw it like an engineer would draw it. So let's say your wavelength is from here to here. Okay, I want you to make a nice reference line. I want you to draw a nice arrow saying, okay, it's from there to here, and then you put the symbol in between. Okay, this also applies to amplitude. So these waves have a certain amplitude. So here it's maybe easier to draw it on this. So the going from here to here, that is the amplitude A. Okay. Okay. So now let's move on here. The wavelength is how far the wave will travel in one oscillation period. So in the process of making this wave, the thing that was vibrating went down and up, and it took one period, it took t of time, one period of time to go down and up. But as it was going down and up, the wave was moving, right? So it's moving. So because of this combination of the time it takes to go up and the fact that the wave is moving to the right, we can figure out that the wavelength, lambda, has to be equal to the wave speed, v, times the period. All right? And the unit, okay, yeah, the units of wavelength will be meters. Now, just plugging in and do a little tiny bit of algebra here, the period is the reciprocal of the frequency. So the wavelength will be v over f, right? I just plugged in 1 over f into t, and I got this. Now, we're talking about mechanical waves here, and mechanical waves come in two types. The first type, one that we've just talked about with the water waves, is called a transverse wave. So in a transverse wave, the stuff that is moving, the water in the previous example, is going up and down, but the waves are moving to the right. And so when you have, one part of something one way and then the other part of whatever it is at 90 degrees, that's called a transverse arrangement. And so these are called transverse waves. So a transverse wave, the wave direction is perpendicular to the motion of the medium. On the other hand, sound waves are called longitudinal waves. You see, in longitudinal waves, the waves are moving to the right, just like before, but the air is not going up and down. The air doesn't move in the transverse direction. Instead, the air vibrates back and forth. And so this motion is aligned with the wave's velocity, and so since they're in the same direction, we call these longitudinal waves. Now I've got some little examples to show you. Okay, so I'm showing you a FET simulation here, and this is going to illustrate a transverse wave. So let's show you that. So you can see that this wave is a pulse, and the wave is, right now it's reflecting back and forth, left and right, but the motion of the medium, in this case the medium is a kind of simulated spring, the medium itself is moving up and down while the wave is going at 90 degrees relative to that. You can see that there's some reflections happening, and we're going to talk about reflections later on. Okay, and here's a video that I made some time ago which illustrates longitudinal waves. They're a little hard to see, but there is a kind of a slinky spring here, and it's suspended by a bunch of threads that are coming down here, so it's free to move left and right. Watch what happens. I'm standing over by the left, and I'm shaking the spring, and you'll see the waves starting to propagate. There they go. So you can see that the waves are going to the right, and the material, the medium itself, the iron loops, are going, they're shaking in the forward direction and then backwards in the same direction as the waves. So this is a longitudinal wave. Longitudinal wave. Now, what you just saw is that a long spring can carry longitudinal waves. That's what I'm showing here. But if you shake a spring up and down, it will be carrying a transverse wave. So in that case, the spring is moving up and down. However, the wave is moving at 90 degrees to that. It's moving to the right while the spring is going up and down. Now, actually, springs can carry transverse waves in two polarizations, which is to say that the shaking could be up and down, or the shaking could be going towards you and away from you, which is basically impossible to draw in this diagram. But there are two options. Up and down is one option, and away towards you is another option. So this up and down would be called vertically polarized waves, and going sideways, towards and away from you, that would be called horizontally polarized waves. Okay. Now let's talk about figuring out the wave speed, predicting the wave speed. Now this can be pretty hard, but in the case of springs and strings, it's not all that bad. So you need to know what the tension is in the string or spring. And you need to know something called the linear density. Now, you've already learned about regular density, right? You've learned that density, like in your chemistry class, means you take a certain volume of a material and you need to know its mass, and you need to know its volume, and the density is the mass over the volume. This is called a volume density. But there are other kinds of densities. So, for example, you might be building a house and putting, let's say, tiling on the floor of the house, and I don't know, maybe the tiles are heavy. Maybe you're putting bricks on the floor of your house, and so in that case, the mass for a unit for area, right? So you have the surface density would be the mass per unit area, and we're here talking about the linear density. And so the linear density is the mass per unit length. Right? Now, volume density would have units of kilogram per cubic meter. An area density would be kilograms per square meter. And linear density would be kilograms per meter. Yeah. That's linear density. So, if we know the tension in the string or spring, and we know the linear density, then we can figure out the speed of a wave in that. So, and it's given by this formula. The wave speed will be the square root of the tension. I could have used the letter T for tension, but the problem is T is getting used for the period for time. So it's better to just use F, the pulling force on the spring. And then here is this is the Greek letter mu, right? So it looks like a U, but with a tail. And so that's the Greek letter mu, lowercase mu. All right. And now actually figuring out this formula is not easy. It requires differential equations, a third, fourth year calculus. So, okay. At this point, I need you to get your book out and start reading chapter 14. So start at the beginning of chapter 14, and when you get to page 457, look carefully at the example, at example 14-1, which is on page 457. Also, on the next page, page 458, there is what do we call it? They call it a conceptual checkpoint. So on page 458, look at the conceptual checkpoint, make sure that you understand that. After you've looked at the book, then go on to the next video. All right?